So one of the power plants that Garland City uses is the Gibbons Creek Power Station. So one of the facts about Gibbons Creek Power Station is that they burn 6,000 tons of coal a day, or 907,000 kilograms of coal. And the amount of heat energy released from the coal is 19 megajoules per kilogram. And then we also know that the power of the station is equal to 454 megawatts. So from this, we can calculate the efficiency of the Gibbons Creek Power Station. So we know the efficiency equation is equal to power out over power in. So we have 6,000 tons times the amount of tons in kilograms, and we get this value right here. And then from this value, we multiplied it with the heat energy of a kilogram per coal, and then we got this energy value over here. From there, we calculated, because this is the amount of coals burned a day, we calculated the amount of energy released within a second to find our watts. And from there, we found out that the amount of energy that the power station is worth over what it could be worth, and then we found out the efficiency is equal to about 38%. So here, once again, using the Gibbons Creek Power Station and also the information we found from the website, we found that 1 kilogram of coal burned releases 2.93 kilograms of carbon dioxide. And so earlier, within the previous problem, we also talked about how 6,000 tons of coal were burned in a day, or 907 kilograms per ton. So here, the unknown, we're trying to find how much CO2 is released within a day and the rate at which CO2 is released. And so for our equations, we have that rate is equal to the change in carbon dioxide over the change in time. So within a day, 6,000 tons are released, 907 kilograms per ton, and that leaves you to this number. And from here, we multiply it by the ratio of number of carbon dioxide kilograms to coal kilograms. And that leaves you with this amount right here, which was about almost 16 million kilograms of carbon dioxide a day. And so using that, we can divide by the amount of time, and that would give us about 185 kilograms per second that's being released by this power plant a day. After talking to one of the workers at Garland City, we found out that 28.82 million gallons of water were pumped on average a day to Garland citizens. Next, we also found out that 22,108 kilowatt hours of energy were used a day for pumping the water. So the unknown we're trying to find is the energy used a day for pumping water and how much energy is used per gallon. A kilowatt hour is the amount of energy, the amount of power in kilowatts that's used for a whole hour, so it's an energy value. So here we have 22,108 kilowatt hours, and then we multiply that to find how much energy would be in seconds. So the watts is joules per second, and we have a second over here using this. Therefore, the seconds cancel out, and that leaves us with kilojoules. And that's how many kilojoules Garland uses a day to pump water. And using that value, we can work it out, and we can find how much watts they use. So that's the amount of joules per second. And they use about 921,000 joules per second to pump water to Garland citizens. Next, we used the 28.82 million gallons of water, and we found that that's approximately 333 or 334 gallons per second within Garland. And using that, we can find how much energy is used per gallon using the watts divided by gallons per second, and then that leaves us with about almost 2,800 joules per. So here we can see the efficiency of the power plant that Garland gets electric from is 37.93%. And earlier we found that Garland uses 7.95888 times 10 to the 10th joules a day just for pumping water, and about 2,800 joules per gallon. And then so to put this into perspective of how much energy is wasted, we found how much energy must be produced for Garland to receive this using this efficiency. So using this value, we divided it by the efficiency, which gives us the total amount that was produced just the total amount of energy that must be produced a day for Garland to pump their waters to its citizens. And so that value turned out to be 2 times 10 to the 11th. And so to put this into perspective, this is about 79 gigajoules, whereas they must produce 209 gigajoules. And so this leaves a waste of about 130 gigajoules, which is a large waste that could be put to use again, right here, again, almost twice. And for here, gallons a day, we waste approximately 4,500 joules per gallon. And so this adds up, and that this could be used to either pump more gallons of water or to be put to better use in other forms or fashions. So the amount of energy needed to pump water across Garland in a day is this amount of energy right here. And so now we're trying to find how much solar panels we would need in order to produce this much amount of energy. For this problem, we know that the incident intensity onto the Earth from the sun is about 340 watts per meter squared. And then for this problem, we're assuming that it's 100% efficiency, not the 38% efficiency of the power plants. So here, what we did was we have two equations, the power equation and the area equation. So what we did was we put this amount of energy back into powers, giving us about 921,000 watts. And we divided that by the intensity to give us the amount of solar panels we need. And we need about 2,709 square meters of panels. However, it's important to note that the efficiency of the solar panels isn't 100%, and therefore if we assume that the efficiency of the solar panels is about 40%, we would need approximately 6,300 square meters, not 2,709.